So let's say that you are given a sorted array. So let's consider a sorted array which contains four elements: 1, 2, 3, and 4. And you need to find the element 4 in this sorted array. Now what you are going to do, now the brute force approach to solve this problem, you will be like, you will search for each and every element in this array, and once you get the element 4, you will just return true, which means that it is present. But let's say the size of the array is too high, that it's greater than 10 to the power 8. So can you solve it in 1 second using the similar algorithm? Now we know that this is a linear search, right? So the time complexity for this algorithm is big of n. So, and we also know that once in 1 second we can only perform 10 to the power 8 operations, right? And hence this will lead you to a time limit accelerator. Now today in this video we're going to talk about the algorithm using which we can solve this problem without getting a time limit accelerator. So hey everyone, welcome back to the channel. This is Abhishek on the other side. I have noticed that most of the people have watched my video but still haven't subscribed to my channel. So as you can see over here, the the percentage of non-subscribed is much higher as compared to percentage of subscribed people. So those who haven't subscribed to my channel yet, do subscribe to my channel and then press the bell icon in order to get the latest notification first. And now, without much further ado, let's start our today's video. So today in this video, we're going to talk about binary search. Now the first question which must be come to your mind, like, what is this binary search? Now this binary search is an efficient algorithm to search an element in a sorted array. By dividing the array in half repeatedly until it is narrowed by it to 1. So what do you mean by it? This statement. So let's consider an array. Now the first condition for the binary search will be like it should be sorted in nature. So each of the elements of this binary search will be sorted. So let's consider sorted array. Okay, so let's consider sorted array. Now this array is sorted. Let's say that we want to find the element 4 in this array. So what are you gonna do according to binary search? Now we know the number of elements for this in this array are 4, right? And the indexes, this is of index 1, this is index 0, this is index 1, this is index 2, and this is index 3, right? So let's consider the low will be pointing to this index 0, low pointer, while the high pointer will be pointing to this index 3. Okay, so this is your high pointer. Okay, so this is low and this is the high pointer. So now what are we going to do? We need to divide this array in half, right? So that means we need to find a mid. So that's the first step. Okay, so let's find a mid. So currently the low is at 0 and your high is at 3. So if you just divide this by 2, and if you just take the lower bound of this, and then it will result me to 1, right? Now, now this is actually pointing me to the index 1. Now the element present in index 1 is 3. So we're going to check whether this 3 is greater than 4. Now we see that 3 is not greater than 4. Okay. Now, so at first actually we're going to check whether this 3 is equals to 4 or not. That is the target element. Now this 4 is the target element, right? And this is the current element which the mid is pointing to. Now we're going to check whether 3 is equal to target element. No, its condition is false, right? Then we're going to change. Now we find that 3 is less than 4. So if the target element is greater than the current mid index, then what we're going to do? We need to move our low point to this index, right? That is mid plus 1. And it is very obvious, right? Because we know that we would not find the element 4 over here, because the 4 is greater than 3, and and hence there is only one possibility, that the element 4 should be present somewhere over here, right? And hence we are going to search only this portion, and hence we are going to just think that this portion doesn't exist, okay? And hence we are going to make our low pointing to index 2, that is mid plus 1. Mid is currently 1, and 1 plus 1 is 2. So currently our low is over here, right? This is our low, and a high is pointing to 3. So again we are going to just see 2 plus 3 by 2. We're going to again find a mid and just take the lower bound. Now we're going to see whether this is actually nothing by 5 by 2, right? Now 5 by 2, which and if you take the lower bound of it, it will becomes 2, right? And here this is going to point to element 4. Now we again want to share whether the element present in index 2 is equals to target element, and we know that 4 is equals to 4, right? And hence this condition satisfies, and hence we are going to return true, because we have found the element which we want to search. But let's say that we want to find the element 5, right? So we're going to perform the similar operation over here, right? Then again we're going to move this low pointer to this to 3, and finally we'll be reaching to 5. But let's say that instead of this we want to find the element 1. Okay, now if we want to find the element 1, now what will it happen? So let's consider when. Now this time our target element is 1, okay? So this is not our target element anymore. So let me just remove everything. Okay, just let me just do it faster. Yes. Now currently our target element is this element, that is 1. So, and this is your index 0, this is index 1, this is index 2, this is index 3, and this is the guy which is the low is pointing to, and this is the guy which is the high is pointing, okay? So again we are going to perform the same operation. We're going to check whether this find a mid of low and plus high by 2. So if we find the mid, it will result me to 2, result me to 1, right? Now we have got 3. Now we're going to check whether this 3 is equals to target. Now we know that 1, the target element is 1, right? So hence this is not equals to target. So we're going to go to next step. Again we're going to check whether this 3 is less than the target element. Hence this condition is also false, as 3 is greater than 1. Now if our current mid element present in the mid is greater than the target element, then we're going to move our high, okay? So we're going to move our high to mid minus 1. That is, we're going to check for this portion, okay? And it is obvious because because we know that 1 is actually less than 3, right? And hence since this array is sorted in ascending order, so we know that we'll get this. There's the possibility of getting 1 on the left hand side is actually more, right? And while the possibility of getting 1 on the right hand side is 0, because because whatever elements are present, okay, on the right hand side is either greater than or equals to 3, okay? And hence we're going to search only for this portion, and we're going to just remove this portion, okay? So this is how the binary search actually works. So now let's analyze the time complexity of binary search. So let's say that we have four elements, okay? Now in such situation, what are you gonna do? You will so let's consider the n to be 4, okay? So we're gonna at first divide this 4 by 2, and hence we are left with 2 elements, right? Again we are going to divide this 2 by 2, and hence we are left with 1. Now when we left with 1, we're gonna stop over there, right? And if this element is equal to the target element, it's well and good. Otherwise we're gonna just going to come out of the loop, right? Okay, now so this is how actually analyze, right? If we try to analyze it, so let's say that we are having n elements, right? So we are going to keep dividing this n by 2. Okay, so at first it will be n by 2, n by 2, then we are going to have to divide this n by 2 by 2, that is we are going to have something like n by 4, right? And then we are going to have something like n by 8. That is we are going to each time actually we are going to divide this n by 2, okay, until until there is only one element. So what we are actually doing, we are actually if we say that we perform k steps, so we are going to end up to something like n by 2 to the power k, and in this condition we are going to have only one element, okay. Now in such situation we are going to stop our binary search. So if you just solve this, so we'll be having something like n is equals to 2 to the power k, okay. And if you log on both sides, if you take a log, so if you take a log over here, log of n, and if you take a log over here also, okay, so you'll be end up to like k, right? This will be log of 2, and this will be your log of n. So what we are getting actually, we are getting actually k is equals to, yeah, k will be something like log of n base 2, right? And hence this is the time complexity for the binary search, okay. Now if you now this is how the binary search algorithm works, and this is the time complexity for the binary search. So now let's code this binary search. Detection of binary search. So at first what we're gonna have, we're gonna actually first take the number of elements, okay, that would be present in our array. So let's consider this to be n. Let's consider an array error which is of size n. Okay, let me just get the input. Okay, before that I need to write using namespace std. So once I have this, so I'm gonna just get the input of error of I. So once I've taken the input, now I'm gonna implement binary search. Let's create a function binary search. Okay, now this function is gonna return me true. Okay, at first I'm going to get the target element, so let me just get the target element tar. So let's take the input of the target element that we want to search. Okay, in the parameters we're going to pass error, and also we're going to pass the target element, and let's get the number of elements present in our array, right? So if it returns true, then we're going to find that present, print present, else we're going to print absent. Okay, simple enough. Okay, so now let's implement this function. So since it is a boolean type function, so its return type will be bool, and so the binary search, this is gonna be int of error, this is your target element, and finally your number of elements in your array. Now at first we're gonna have the low pointer which will be set to 0, and the high pointer and our high pointer will be set to n minus 1, right? Then we're gonna have a condition as this low should always be less than equals to high. Okay, that's our condition. Next we're gonna have the mid element, so let's take to consider the mid as a low plus high by 2. Now for this we're gonna find the mid index for this array. Then we're gonna check whether our mid, that is error of mid, is equal to tar or not. If it is tar equals to target, then we're gonna just return true, which means that it is present. Else if our error of mid is actually less than tar, okay, yeah, if it is less than tar. Now what does it mean? It means that so let's consider this example. So let's say suppose we are having some array like elements 1 2 3 and 4, right? Now let's say that our target is 4 and our mid is pointing to element 2. Now in such situation what are you going to do? We need to check these elements, right? And hence we are going to just ignore this one, all these ones, because we know that we never find the elements over here, right? Because this array is sorted in ascending order. So what we're gonna do, we need to make update our low as mid plus 1, right? And if this condition is not satisfied, then we're gonna make update our high as mid minus 1, right? And if the element is not present, then we're gonna just return false, okay? So let's get the input. So let's take 5 elements, and the elements are 1 3 5 6, and let's consider it to 7, and the element we need to find is 6, okay? So let's run this code. At first let me comment, yeah, run this code, commit and run. Let's see, yeah, it is saying present, right? But let's say that if we search for element 4, which is not present, right? And if we just run this code again, let's see what it said, absent, right? And hence this is how our binary search actually working. Now this algorithm is actually taking the time complexity for this algorithm from here to here is actually big of log of n, right? And since we are not using an extra space over here, so the space complexity is big of 1. So that's how you implement a binary search. So now let's try to go deeper into binary search by solving some problems using binary search. So the first problem we're going to solve is square root of x. Now it is a easy level question from LeetCode. The question states that you are given a non-negative integer x, compute and return the square root of x. So we are given a non-negative integer x, right? And all you need to do, we need to find the square root of x. Now there is a condition. Now since the return type of an integer is an integer, the decimal digits are truncated and only the integer part of the result is returned. So if you consider this example, that is 8. Now the square root of 8 is 2.8242 and something, right? Now, now according to the question, we are going to not consider this part, the decimal part of the integer. We are not going to consider. We are going to only consider the integer part, right? And hence we have to return 2. So now let's see how using binary search we can solve this problem. We can easily solve this problem using Sqrt function, that is Sqrt of n. Sqrt, by writing Sqrt of n, right, in C++, we can solve this problem. But this time complexity for this algorithm is like square root of n, okay, and which may actually lead me to a time limit exit error if the input size is too high. Now One of the optimal way of solving this is using binary search. Now, because in binary search we can solve it using big of log of n, right? So let's consider that the value of n is 8, right? So according to the question, its output will be 2, right? Because it is 2.82 something like that, right? Something, and hence 2.82 something, and hence it's and since we are only considering the integer part, and hence we don't have to think what is there in the decimal part, right? So let's see how we can actually solve this problem using binary search. Now we know one thing that this is now the square root of 8 is somewhere between 0 to 8, right? So and hence our low will be 0 and while our high will be 8. Okay, so we're going to consider this, right? Now we know that binary search occurs when our array, when the elements are sorted. Now we know that it is already sorted, right? Because after 0 it comes 1, right? And then we'll have 2, so it will be 1, 2, 3, 4, 5, 6, 7, and 8. So hence these are the elements which is actually present in the range of 0 and 8. Okay, so and we know that the square root of 8 is somewhere present between this 0 and 1, 0 and 8, right? So according to Vanessa, what we're going to do, we need to find a mid element. So let's find a mid by considering this 0 plus 8 by 2. Now this will give me 4, and which is nothing but this element, that is 4. So now we know that in order to find the square root of any element, so the formula will be somewhat like x square. Now let's consider this x to be square root of that element. X square is equals to n, right? And n is the target element, that is here we can consider it to be 8. So we can actually write this formula as x is equals to n by x, right? Where we'll be taking the lower bound of this value. Okay, so we can also write this formula as this, right? X is equals to lower bound of n by x, right? So hence we're going to check now this 4. Now we can consider this 4 to be x. Now we're going to check whether this 4 is less than equals to, okay, 8 by 4. Now we know that 8 by 4 is 2, right? So is 4 less than equals to 2? False, right? Now when we find that 4 is not less than equals to 2, what are we going to do? We need to move our high pointer, which is currently pointing to the element of 8, because we know that whatever elements is present in this section, that is from here to here, is will never be our answer, right? Because we know that 4 square is 16 and 16 is higher than 8. So hence 4, 5, 6, 7 or 8 can never be our answer. So we need to move our high pointer. Now the high pointer will be pointing to this element, this tree. So and hence our high pointer is nothing but mid minus 1. Now what is our mid? Now our mid is 4, and if you just subtract it by 1, now high will be 3. And hence our high is pointing to this element, that is 3, while our low is pointing to element still at 0. Okay, next we are going to again find find the mid element, that is 0 plus 3 by 2. and if we consider the lower bound, then we're gonna get 1. Okay, now again we're gonna check whether this 1 is less than equals to a less than equal. Now this time, yeah, 8 by 1, right? Now we know that this condition is satisfied, right? Now since this condition is satisfied, we're gonna have also an answer variable. Now initially the answer is actually this variable is pointing to is nothing but 0. Okay, so once this condition is satisfied, we need to update this answer variable. So we're gonna update it to the mid, that is, now it will be updated to 1. Okay, because this condition is satisfied. Now since this condition is satisfied, so we know that 0 is also less than equals to this 8 by 0 something. Now we know that 8 by 0 is actually is gonna give me an error, right? So we are not going to consider that. So if it reaches to 0, we're not going to consider that. Okay, now 0, when it is 0, it is always satisfied. Okay, so we know that whatever present in this range is also satisfied, right? And hence we need to move in this direction. And now we're going to update our low pointer. Currently our low is pointing to element 0. Now it will point to element 2, that is, low will be nothing but mid plus 1. Okay, now currently our mid is 1, right? So our low will be 2. Okay, so now our low is 2, while our mid is actually 3. High is actually 3. Okay, so again we're gonna find the mid. We're gonna write 2 plus 3 by 2. Now 2 plus 3 is nothing but 5. So if you consider lower bound and just divide this by 2, 5 by 2, it is 2.5. So if you consider lower bound, it is 2. Now again we're going to check the condition that whether 2 is less than equals to 8 by 2. Now we know that 8 by 2 is nothing but 4. Okay, and hence 2 is less than equals to 4, right? And hence again we're going to update this to 2. Now since we have updated this to 2, we need to move our low pointer. Now our low pointer will be again mid plus 1, that is, now it is going to point to this element, that is high. So now our low will be 3. Now again we're going to find a mid element, that is, we're going to write 3 plus 3 by 2. Now 3 plus 3 by 2 is nothing but 3, right? So again we're going to check whether this 3 is less than equals to 8 by 3. Now if you consider the lower bound of this, right, then it will result me to 2, right? And we know that 3 is not less than equals to 2, and hence we are going to move our high. Now our high will be moving to mid minus 1, that is, it will be pointing to this element 2, and our low will remain in 3. Now when our high is less than low, okay, now in this situation we are going to terminate out of this loop, and we are going to return our answer, that is 2. Okay, and hence our answer will be 2. So this is how the algorithm works. Now the time complexity for this algorithm will be nothing but big of log of n base 2, right? Because we have considered the binary search algorithm, right? And while the space complexity is big of 1, because we are not using an extra space over here, as you can see. So now let's try to code this algorithm. Now there is a corner case for this problem. The corner case is when our n, okay, when our n is less than equals to 4, less than equals to 1, sorry, then we just need to return our n. Okay, because it will lead me to an runtime exception, right? Because over here we are actually dividing this n by x, right? So if we consider the low to be 0 and our high to be 1, and if you just divide this by 2, then it will lead me to 0. Now we know that whenever we divide any integer by 0, then it will lead me to infinity, right? And because of this infinity, there will be a runtime exception. So in order to handle that exception, we need to have a condition like when our n is less than equals to 1, then we just need to return this n. So that is the only corner case that we need to handle before implementing this binary search approach. So let's first handle the corner case by writing it as like x. If our x is less than equals to 1, we just need to return x. Okay. Now here we can consider x to be n. So let me just rewrite this to be n. Okay. So that you don't get confused. Yeah. Now it is n. And now we are going to implement our binary search. At first we are going to have a low pointer. Now this low pointer will be currently pointing to 0. And next we are going to have a high pointer. While this high pointer will be pointing to n. Next we are going to have a while loop. Now in the while loop we are going to check whether our low is less than equals to high. Now if this condition satisfies, then we're going to move inside this while loop and we're going to have a mid. Now in this mid we're going to find a middle element, right, as low plus high by 2. Now this would give me the middle element. Now once we have find the middle element, we need to check whether our middle element is less than equals to n by mid. Now you can consider this mid to be x, as we have considered in our explaining part. Now if this condition is satisfied, then we're going to have a answer variable. Now in this answer variable, currently the answer variable is initialized to 0, so we're going to update it to mid. Okay. Now next we're going to make our, now if this condition is satisfied, we need to update our low to mid plus 1. And if it doesn't satisfy, we're going to go to else part. Now in the else part, we're going to update our high as mid minus 1. So that's it for the algorithm. So next I'm gonna coming out with the while loop. I'm gonna just return answer. So I think that's it. So let me just run this code, see if it works. So it is giving me accepted. Let me just submit it. Okay. Yeah, it is accepted. So I hope that you like this video. If you like this video, do give a thumbs up to the video, share it with your friends and subscribe to our channel and press the bell icon in order to get the latest notification first. And if you have any doubt, do comment down in the comment section below and I will see you in my next video.